we were discussing quasi-regular mappings. And these are mappings U of the W1n, omega contained within Rn, into Rn, such that we have that the operator norm of the matrix, that is the gradient to the power n, is bounded by some constant q, big and equal to 1, times the determinant of the gradient. So implicitly in this, we have the determinant is non-negative almost everywhere. Okay. So maybe I just put the aside here. So when we write this, we're going to mean the sup of V belongs to Sn minus 1. This is what I call the operator norm of the matrix. Okay. And the picture was this. So if we take, let me just underline this. So then if we take the gradient for some arbitrary point for which it exists, mapping the unit ball, we'll send it to, it will send it to some kind of an ellipse type shape, right? And the volume of this, as we discussed, is the determinant of the matrix. And the operator norm, just from the definition, gives us the radius of the smallest ball that contains the image of the ball, right? So this is the operator norm of the gradient, like this, right? So this guy here is the volume of the smallest ball that contains the image of the unit ball, and this is the volume of the unit ball, right? This guy here is always bigger than this guy, just from the pictures. But we want to constrain it to be not too much bigger, so we have this constant q here, q bigger than equal to 1. Write that here. So let me put this in. So we say U is Q quasi-regular if this is true, and the larger the Q, the more we allow some kind of long thin ellipse. And if Q equals 1, then that forces the image of the unit ball to be a ball itself, and we're back in the space of conformal mappings. Yeah? So it's more restrictive as Q tends to 1. Yeah? Cool. All right. So this is a substitute for holomorphic mappings. This is a much wider class of mappings, obviously, and there is a deep and non-trivial theory of such mappings in higher dimensions, which is part of the reason for its creation, arguably the reason for its creation, discovery. So a couple of the main theorems of complex analysis that we're very familiar with actually hold true for quasi-regular mappings, and these are the following. So Q quasi-reg mappings open and discrete, and I'll say what this means in a minute. So open means that the image of open maps are open. So if U contained within omega is open, then U of omega is open. U is a very bad choice. Let's call it this thing. Let's call it O. That is open. And we know this from, no, this is true about holomorphic mappings. This is the open mapping principle, okay? And discrete means that if we take any zeta inside the image of omega, then u to the minus 1 of zeta is at most countable. So it could be finite, but it's at most countable. And u to the minus 1 of zeta has no cluster points in omega. So if it is infinite, then it might have a cluster point, but the cluster point has to go right off the edge of the domain, right? And we also know this from complex analysis, so let us remind ourselves of some complex analysis. So if U is holomorphic, then any zeta belonging to this guy, consider the mapping, let's call it G of Z minus, let's call this zeta 0. This is also holomorphic. And u to the minus 1 of zeta is the set of zeros of total nonsense. Okay, I need to engage my brain. Consider G of Z to be defined to be equal to U of Z minus zeta 0. Then this set is exactly zeros of G, and G cannot have a cluster point of zeros in its interior, or if it did, then all the terms of the Taylor series would be wiped out, right? So, and everybody happy with that being true, right? Okay, cool. Cool. So these are some of the main properties about quasi-regular mappings that we will discuss and ultimately prove. And in 2 dimensions, this stuff follows from a much stronger theorem called the Stoid of Decomposition. And I should have checked how to spell Stoilow before I started. All right, so do not remember how to spell Stoilow. I'm going to approximate it. So if n equals 2, these follow. From Stoilow, it's definitely not like this. Composition, which I'm about to explain. So, what is the Stoid of Decomposition? This is where we can find a quasi-conformal mapping, which means a quasi-regular mapping that's invertible. So, a quasi-conformal mapping i.e. quasi-regular that's invertible. Such that, let's call it W, and the holomorphic mapping from the image of W into the image of U, such that we can do this decomposition, that U of X is equal to phi of W of X, like this. And this is best explained with a picture. We have our mapping which takes our region, say omega, into the image of omega under U. So this is omega, this is the mapping U, and obviously this is U of omega. This is our quasi-regular mapping, right? And we have a mapping W that is invertible, that maps this thing to, let's say, this thing, and this is W of omega, like this, okay? And then we have this holomorphic mapping that maps from W of omega onto the image like this, right? So that's exactly this decomposition here, yeah? And note the following, that if we take the gradient, then we have the gradient of this thing times the gradient of W of X. Okay. Now the gradient of a holomorphic mapping, as you know, it's just a conformal matrix, right? But as we've just discussed, the gradient of a quasi-regular mapping absolutely doesn't have to be conformal. It's allowed to distort the unit ball into things that are not too thin ellipses, right? The gradient, you know, the ellipse can be of any size. The only constraint that this is doing is it's preventing it being too thin, you know, too long and too thin. You know? So this guy right here is a conformal mapping, a conformal matrix in R2, right? So it's just a lambda times a rotation. Yeah? Whereas this thing is actually doing something that's going to change the geometry of the unit ball into some different shape. Yeah? So from this, it's not it has to be the case that this guy is changing the geometry of the unit ball to a similar shape, right? Because all this thing is doing is rotating and stretching stuff. Yeah? Yeah. So how this theorem actually works is that we are able to take something that we're able to take a function that is not invertible, that it's potentially wrapping around itself in lots of different ways, and at each gradient we see how it's distorting the unit ball. We see the kind of shape it's going to, and we can find a quasi-regular mapping that for each x does the same kind of distortion, that distorts it to a similar shape. Okay, and that's a very deep and very big theorem that we can find such a W. But if we can find such a W, then it's not surprising that we have a holomorphic mapping, because we can just go back like this. We can go like this and then like this, and that's how actually we define the holomorphic mapping. Yeah? And then such a mapping from here to here will indeed send the unit ball to something which is of the shape of a ball. And that is not something you can see in your head, but something that if you believe me that dW does recover the way that the shape of the unit ball is distorted by du, then it should seem intuitive that this mapping we get phi from going back and then back will indeed be something that just sends balls to balls. Okay? So the real heart of this is that we can find a W which distorts the unit ball in the same way that the gradient of u distorts the unit ball, but W will be invertible. And that's the so-called Beltrami Theorem. That's what's sometimes called, and it's a good name, the Measurable Riemann mapping theorem. And that will be something we're going to prove, and that will be one of the highlights of the course. And that's the key thing behind this decomposition right here. As I erase, I want you to think about why we have an open mapping if we have the Stoilow of decomposition. And if you figure that out, then tell me why we have a discrete mapping if we have a Stoilow of decomposition. Okay, so Stoid of Decomposition. For Q quasi-regular, we have that u of x equals phi of w of x. This phi is hollow, and w is quasi-conformal, q quasi-conformal. And what I should have also said is that it's a theorem, and it's a non-trivial theorem, quite a non-trivial theorem, that if you have a quasi-conformal mapping, it's actually continuous, it's even Holder, right? So it's a theorem that Q quasi-conformal mappings continuous, actually Holder. And the Holder exponent depends on the Q, and we will get into that later. Yep. Yep. And so obviously that implies that U is also continuous from the Stoid of Decomposition. Tell me why it's open. Why is it open? So let's draw a picture again. So we have our region omega. It's mapped to U of omega. Okay. We have W in an invertible way mapping it to this. And then we have a holomorphic mapping phi, like this. Okay, so why is it open? From see that U is open because what? If we have an open set, call it O, inside here, yeah? If we map it onto here, will this thing be an open set? If we consider W to the minus 1 from W of omega into omega, right? Tell me properties about this mapping. What do we know from the fact that W is quasi-conformal? Well, the gradient of x is W to the minus 1. That's multivariable calculus again, right? Yeah. How will the inverse of dW change the unit ball? No. So look. So dW of x is sending the unit ball into something that isn't too long or thin, right? So if we do polar decomposition, which means we decompose it like this, dW of x is equal to a rotation, let's call it r of x, and a positive definite symmetric matrix. Have you guys all seen polar decomposition of matrices? Perhaps not. Some of you yes. Put a thumbs up if you have seen that. Not everybody. Where r of x inside rotations. I mean, this is true in n by n, but we're in 2 by 2. Okay, and then symmetric matrix we can diagonalize. Yeah, so if we diagonalize it, then what we see is that when we consider the action unit ball, we're first going to rotate it, then we act one with the diagonal matrix, then we rotate again, then we rotate again with this guy, right? So the actual distortion is controlled just by the eigenvalues, yeah? Actual distortion is controlled just by the eigenvalues. Let's write what this is. This is polar decomposition. Okay, so if we have a matrix, a diagonal matrix like this, okay, that doesn't distort space too much, right? What's it going to do? Well, that means the ratio of these guys is controlled. The biggest guy divided by the smallest guy is going to be controlled by the Q. Yeah? But the inverse of this guy is a to the minus 1, 0, b to the minus 1. Yeah? And that too will have its will control how it distorts space, right? If we have I don't want to try and do the algebra in my head or in real time, but I think it's kind of trivial. So if, well, let's do it. If b is bigger than a, then we've got to have that. So what do we know? We know that the operator norm, which is b squared, so assume b is bigger than a. So b is bigger than a. So then b squared is less than q of ab, right? Which means that b over a is controlled by q. Yeah. And that would mean that a to the minus 1 is bigger than b, so then a to the minus 1 over b to the minus 1 is equal to b over a, and that thing is also controlled by q, right? So then we'll have the same property for the inverse mapping, yeah? Okay, so since a to the minus 1 is therefore bigger than b to the minus 1. So these are positive definite, these are positive numbers, a and b. Yeah? So exactly the same distortion control occurs for the inverse as does for the actual matrix. Yeah? Cool. So we have that this guy has got this property that it's not distorting space too much, so satisfies same inequality that the operator norm, this one's correct. The operator norm of dw to the minus 1 of x squared is bounded by q of determinant w to the minus 1 of x, i.e. it is quasi-conformal too. So, well, it's quasi-conformal in the sense the way that the matrix is distorting. It's a non-trivial thing to show that actually the inverse is insoluble space W1n. So, assuming we know that w to the minus 1 belongs to w1, 2 in this case, then w to the minus 1 is q quasi-conformal yeah, therefore continuous. And so we have what we want, right? So therefore, the image of W of O has to be an open map because, just as Josh was saying, that is the same as the inverse of O with respect to W to the minus 1. And that thing is and that thing is a continuous mapping. You know, the inverse of a continuous mapping is the pullback of an open set with a continuous mapping is open. All right, so it's open. Yeah, there is, yeah, for sure. Okay, so this is a general philosophy of mine, is to avoid, specifically to avoid general topology, but to avoid using theorems if I possibly can. So so yes, this is, you have to come up with quite an exotic example. Well, not quite an exotic, but a somewhat exotic example to find a bijective mapping whose inverse is not continuous, right? So yeah, this is not a surprise, but yeah, I'd rather give an elementary reason and also tell you a bit more about Quasi. But thank you about this this fact. Yeah, this is a generally not, you don't need to do all this stuff. You can just apply general theorems from general topology. All right, so once we know that W of O is open, then we're fine, because then U of O is just the image under phi of W of O, and phi is an open mapping. Yeah? Thus, W of O is open. And U of O. Did I say what O was? Not yet, so. Thus, for any open O contained within omega, so it's open. Cool. All right, now we're going to see that it's also discrete. So the inverse of any point here will be at most countable, and any cluster point goes off the edge, right? Looking at this diagram, try and tell me why you see that it's discrete. Good. So it's also discrete, so in the sense that, oh, actually, since I just said, so if we pick some zeta 0 inside here, we also know discrete. So pick zeta 0 belonging to the image like this. Yeah. Then we're going to try and we're going to try and get an understanding of the set of points mapping onto this. So note the following, that the set of x such that u of x is equal to zeta 0, same as the set of x such that phi of w of x is equal to this thing. So change of variables, let's let y, if we let y be w of x, then obviously w to minus 1 of x of y is equal to the x, so it's the same as the set of w to the minus 1 of y, such that phi of y is equal to 0, and running out of space, we'll put it over here. That's the same as w to the minus 1 of the set of w, such that phi of this thing is equal to zeta 0. Yeah. And we know that when we pull back into here, the set of points that are mapped onto zeta 0 by phi is a discrete set. So it doesn't have any cluster point except at the boundary. Yeah? Except at the boundary. Yeah? So take a set that is compactly contained within omega. So take pi compactly contained within omega. So this means that pi is contained within a compact set which is inside omega. okay? i.e. pi is contained. All my stuff is overlapping. In compact set in omega, so there's some specific distance between pi and the outside. Then, because W is continuous and its inverse is continuous, we know that W of pi is compactly contained within the image of W of omega, right? And so W of pi intersect sort of this is equal to z to 0 is finite, and then we just pull it back, and therefore pi intersect W to minus 1 of the set of y, such that phi equals z to 0, which is equal to pi times the thing that we're interested in, the set of x, such that u of x equals z to 0 is finite. Yeah. Yeah. And that's just writing out in detail what Heigo quickly told us, that if we have an inverter mapping like this, then since this guy is discrete, then you'd expect that this structure is preserved, right? You can't have no cluster points occurring except as they go off the edge of the boundary, and then somehow pull back and have a problem, right? Because it's a bijective continuous mapping by homeomorphism. Yeah. Yeah. Cool. Everybody happy. Yeah. So the Stoid of decomposition is a lot more powerful than these two main properties of quasi-regular mappings. And the Stoid of decomposition is only known in 2x2. I mean, there's probably a theorem in high dimensions, but it just isn't been proven. Or maybe there isn't much of a, maybe there isn't a strong theorem, but there isn't a known theorem in high dimensions. And probably if such a theorem exists, it isn't going to be as strong. Yeah, I mean, yeah, for sure there isn't such a theorem, because holomorphic mappings in higher dimensions are just Mobius, so forget everything I just said. There isn't an analog in higher dimensions. So Stoid of decompositions are very strong things, and yeah, and now we're going to start to set up the algebra to understand the linear algebra to put us in a position to prove the Stoid of decomposition. Well, okay, so linear algebra. Hope that's how you spell algebra. Okay, so first we have the decomposition of 2x2 matrices into conformal and anticonformal. So and this is an extremely powerful thing. So if you ever end up doing calculations with matrices in 2x2, it's very much worth your while to consider decomposing it into conformal and anticonformal, because somehow a lot of the things, a lot of the calculations become much more transparent with this. Okay, so how does this go? So if we take a matrix A, B, C, D, we can write it as 1/2 A plus D minus C minus B, C minus B, A plus D. This is a conformal matrix plus this thing, so we're going to have A minus D, we're going to have B plus C, B plus C, and then minus A minus D. Right, so if you look at this, then we get back everything that we want, right? This is true. This is a true thing. Yeah, and this guy belongs to conformal matrices, and this guy is anti-conformal. So we're going to write this as, I don't know if this is standard notation, but we're going to write it like this. Okay, so this guy has the property that if we take the determinant, it is negative, right? In fact, it's just like a conformal matrix after we multiply it by reflection. Yeah. So note, if we're going to take this thing to be 1, 0, 0 to the minus 1, this diagonal matrix, so then if A belongs to the anti-conformal, then A times this reflection belongs to the conformal. Yeah, just a little exercise. I guess you can do it in your head. And note also that this is a space of conformal matrices and the space of anticonformal matrices in 2 by 2. They're linear subspaces, right? So let's write them down. Conformal matrices are things of the form A minus B, B, A. A, B belongs to real numbers. And anticonformal are things of the form A, B, or maybe just use different letters. C, D, D, minus C. C, comma, D belongs to real numbers. Okay. So if you take the dot product of any two matrices, so if you take inside these different spaces, so if A belongs to conformal, and then B belongs to anticonformal, then the dot product of the matrices, which means dot producting every entry just like it's a vector, right? It's going to be 0 because this guys will kill and these guys will kill, right? So this is equal to 0. So these are orthogonal subspaces, right? So conformal and anticonformal, which is part of the reason these things turn out to be so convenient. Orthog subspaces that decompose. So we saw orthogonal decomposition of 2 by 2 before when we decomposed into skew and symmetric matrices, right? But in that case, symmetric matrices are the 3-dimensional subspace, skew in 2 by 2 are just a 1-dimensional subspace, right? This is a decomposition into two-dimensional subspaces. We also know that, I mean, this is something I talked about in complex analysis, that the field of conformal matrices is isomorphic to the field of complex numbers because multiplication and addition are exactly the same in these things. So it's just that's a kind of curiosity for us. Well, not exactly curiosity, but I mean it's pretty important, but it's not essential for what I'm about to say. So note that if we define, let's say, P from conformal into the complex by P of A minus B, B, A equals A plus IB, then addition's the same and multiplication's the same. This is a field homomorphism. So the whole, I mean, this is something I talked about in my class, the whole study of complex analysis of functions from complex numbers to complex numbers is identical to the study of mappings from the conformal 2x2 matrices to the conformal 2x2 matrices. We can avoid talking about I completely in complex analysis. It is just that it's convenient notation for this field, right? The point is that there exists a two-dimensional field that has a natural commutative operation of addition and multiplication, and those are the complex numbers, but it's also the conformal matrices. All right, so these things are cool. A couple of cool identities. That if we, okay, so some notation perhaps. If this thing is A, then we're going to define this thing to be this. So when we put a square brackets and a little subset C, that's the conformal part of A. And we're defining this thing to be this, the anticonformal part of A. Okay? So we have this decomposition of A into the sum of its conformal and its anticonformal parts. Yeah? And these mappings A to the conformal and A to the anticonformal, they're obviously linear mappings. Yeah? Obviously linear mappings. Yeah? In fact, since these are subspaces, these are actually projections. These are orthogonal projections. Yeah? Cool. So we have a couple of identities that if we take the determinant of A, it turns out to be the determinant of the conformal part plus the determinant of the anticonformal part. So obviously it's hopelessly false if you decompose A into two matrices. You can't add determinants. Determinants are not linear things, but it is true when we do this decomposition into conformal and anticonformal. And the determinant of conformal and anticonformal is just the same as the norm of the matrix, the Hilbert-Schmidt norm of the matrix squared, because if we take the determinant of A minus B, B A, this is A squared plus B squared, which is the same as what I call the Hilbert-Schmidt norm of A minus B, B A squared. Yeah? Yeah? So this thing turns out to be, this determinant will be a positive thing, but the determinant of the anticonformal is negative, right? So if it's anticonformal, then we're going to have this, like this, right? And therefore it's going to be minus this if it's anticonformal. So we have that this is the same as the Hilbert-Schmidt norm of AC squared plus Hilbert-Schmidt norm of minus the Hilbert-Schmidt norm. Right? So anticonformal matrices have negative determinants, so it's like, I don't find words, but this fact is somewhat natural given that anticonformal matrices have got negative determinant. Right? So we have this neat identity, not essential for our purposes, but I want to say it because we're going to use it later, and it's also just quite neat. It's one of the reasons that calculations on 2x2 matrices with conformal anticonformal is very convenient. Another thing, well, this is the thing that we really care about. So we're going to define. Okay, I'm over time. I want to finish the sentence. Leave whenever you want. We're going to define the Beltrami coefficient of a 2x2 matrix. I realize this is not how you spell this word. Anyway, the Beltrami coefficient of A belonging to M2x2 is, so by the following. We are going to take the anticonformal part of the matrix. We are going to compose it with a reflection I like this. This will now give us a conformal matrix. And any conformal matrix can be related to another with composition with a conformal matrix. In other words, I mean, it's just the same as saying conformal matrices are fields. So we're going to define this to be like this. Like this. The Beltrami coefficient, let's write this mu, no, that's bad structure. The Beltrami coefficient is like this. Beltrami coefficient, written as mu of A belonging to the two-dimensional conformal matrices, like this. So this makes sense as a definition because, again, this thing here is a conformal matrix. This is a conformal matrix, so we can just compose on the other side, right? Because it's a field, right? So this makes sense as a definition. It's a conformal matrix, so it's just containing it's just an element of a two-dimensional vector space. It just contains two coordinates. Yeah. And this is a linear operation, right? So this is a linear projection. So notice that if we take lambda times A, and we do the decomposition, so it's lambda times A conformal plus lambda times A, that's anticonformal, anticonformal. Okay, because these are linear, we can just pull them out, right? So this is I did it the wrong way around again. This is C. Right. The polar decomposition is unique as it's a linear projection onto orthogonal subspaces. Uniqueness is clear. So in particular, we can just pull out these things. So lambda of the anticonformal is equal to lambda this. I mean, I guess I didn't have to write all that stuff. I could have just said directly that it's a linear mapping, but whatever. We're going to use something like that again. And lambda of A of C, like this. Yeah. So if we consider lambda of A in the definition of Beltrami coefficient, we can just pull out the lambdas from it, right? And it's not going to change anything. Yeah. So this implies that actually the Beltrami coefficient doesn't notice when we dilate something by some lambda. Okay, just from the definition, it just doesn't notice it. This Beltrami coefficient is uniquely defined by this, and it can't tell the difference if we have A or lambda times A. Okay, bit more subtle is if we rotate a conformal matrix, let's see what happens. So if we rotate an arbitrary matrix A and do the conformal anticonformal decomposition, let's see what happens. So I'm going to write the same line. So maybe start with telling you what R is. So if R is a rotation, then A, or rotation times R of A can be decomposed into R of A conformal, and then R of A anticonformal. So that's the standard decomposition, but we can also just take our decomposition and multiply R on the left-hand side and see what that gives us. So that's also the same as just doing R of A conformal plus A anticonformal, like this, yeah? And then if we multiply this through, I want to get rid of the whole thing. this is the same as R of A conformal plus R A anticonformal. And again, the decomposition is unique. And this thing here, for sure, is a conformal matrix because it's just rotations times a conformal matrix, right? And it's also not hard to see that this is just an anticonformal matrix because this guy, you can think of as you can write this as I times I, right? And doing that, so on the left, you can put here I times I on the right-hand side, and then you can see that this thing is itself an anticonformal matrix. You know? So rotating on the left-hand side in an anticonformal matrix is still an anticonformal matrix, is what I'm trying to say. You know? And the decomposition is unique. So that means that this conformal matrix has to be the same as this conformal matrix, and this anticonformal matrix has to be the same as this anticonformal matrix. So this implies that R of A conformal is equal to R of A conformal, and R of A anticonformal is R of A anticonformal like this. That's what it implies. Okay? We can pull out the rotations from this. Yeah? Which means that in this thing, we also do not see rotations because we can just write like this. So leave whenever you want. I just want to complete these basic identities to have a clean place to start from. And then this thing is the same as R of A anticonformal times I equals mu of R of A, and then R conformal like this. Conformal matrices commute, right? Multiplication is commutative when we have conformal matrices. So we can pull out the R all the way here and then just get rid of it. So that implies that we actually have this. Which means that this thing is exactly the same as this thing. Yeah? So because we don't have any of this stuff in high dimensions. We don't have a anticonformal decomposition in higher dimensions. So all of this stuff is, oh yeah, everything is dimension 2. You know? This is dimension 2. Yeah, I mean, these are all 2x2 matrices. Okay, so the moral, well, more than a moral, true fact. So mu of A doesn't notice dilations or rotations. Rotations. Okay. It doesn't notice dilations or rotations. So if you take your matrix and it's deforming the ball into some sort of ellipse, and it might be like whatever, yeah, then mu of A isn't going to detect the size of this. It's also not going to detect where you rotate it around. Yeah? It's going to be this 2 vector that just understands the shape. Okay? Yeah? Compare this with the symmetric part of the matrix that you get from polar decomposition. So when you do polar decomposition, so compare with polar, when we write A is equal to a rotation times S, where S belongs to symmetric in 2x2, then symmetric 2x2 are a 3-dimensional space, right? And then this thing will not know where you've rotated it to, but it will understand the shape and it will understand the size. Yeah? So S understands shape and size. Shape and size. And mu, let's write this to show you, it's going to do mu of A just understands shape. Okay. So, as you can imagine, that is a relevant thing for our study, right? Because when we are considering quasi-regular, quasi-conformal mappings, the restrictions are on the shape, not on the size, not on the rotation, anything like this, you know? So we're going to be able to formulate things about quasi-regular, quasi-conformal mappings in terms of things to do with the Beltrami coefficient. And ultimately, we are going to be able to extract that information, and we're going to be able to take a quasi-regular mapping, extract its Beltrami coefficient, and then find a quasi-conformal mapping with the same Beltrami coefficient. That is the so-called Beltrami equation. So when you see it in the books, it's written in complex language, in complex analysis language. It doesn't look as unless you're very familiar with language, it doesn't look as transparent as the 2x2 stuff. So I prefer to formulate in 2x2. But that is the heart of, as some of you can already see to some extent, that is the heart of the Stoid of Decomposition, being able to find a quasi-conformal mapping with the same Beltrami coefficient as a quasi-regular mapping. That's a very deep theorem. And once we have that, then decomposition follows, and all these other cool things follow. Cool. All right. So next class, I'll talk about Ivanich spheric, Stoid of Decomposition, Stoilow Theorem, and then we'll start to develop machinery to prove the Stoid of Decomposition for just Q quasi-regular mappings. Spheric Ivanich has a much more general theorem, which uses the theorem for Q quasi-conformal mappings, but pushes things further. All right, that's it for today. Sorry, I've overrun. Have a great day. See you all on Friday. All right, bye-bye.